Hey everyone, welcome back to Chem Story. Today we're diving into molecular symmetry. At first, it might just seem like a geometry concept, but trust me, it's way more than that. Symmetry actually plays a significant role in organic chemistry. So why does symmetry matter? Well, it helps us understand some key concepts, like why certain molecules rotate plane polarized light while others don't, or why some compounds are superimposable on their mirror images while others aren't. Once you start spotting symmetry in molecules, you'll see how it helps explain their optical activity and even their overall shape. All right, let's dive right in. Molecular symmetry is all about how a molecule can be transformed but still look the same. It's not just about seeing atoms connected. It's about spotting patterns that define the molecule's structure. Symmetry elements like rotation axes or mirror planes help us classify molecules in a more systematic way. Once you get the hang of it, recognizing symmetry makes it much easier to understand molecular shapes. So, why is symmetry such a big deal in chemistry? Well, it actually affects a lot of things like polarity, reactivity, and even how molecules interact with light. One of the most important areas where symmetry comes into play is spectroscopy, especially IR and Raman. Symmetry helps us figure out which molecular vibrations are actually detectable. And when it comes to stereochemistry, symmetry plays a big role too. You might think that if a molecule has chiral centers, it's automatically optically active, but that's not always the case. Sometimes, even if a molecule has chiral centers, it doesn't rotate plane polarized light. That's because its internal symmetry cancels out optical activity. A great example of this is meso compounds. So symmetry isn't just a visual concept, it really shapes how molecules behave and how we analyze them. Once you get the hang of spotting symmetry, it makes understanding these concepts way easier. To really get symmetry, we've got to talk about two key ideas: symmetry operations and symmetry elements. So, what's a symmetry operation? Basically, it's any transformation that leaves a molecule looking exactly the same as it did before. Think about rotating, reflecting, or even flipping a molecule. If it still looks identical after you do that, then you've performed a symmetry operation. It's like giving the molecule a little makeover. But when you're done, it still looks just like it did before. Now, these symmetry operations work because molecules have built-in symmetry elements, things like axes, planes, or points that make these transformations possible. For example, if a molecule looks exactly the same after you rotate it around a certain axis or reflect it across a plane, that means you've just used a symmetry element. It's basically the invisible framework that makes symmetry possible. Understanding these elements is super important because they help us predict how molecules behave, especially when it comes to stereochemistry, spectroscopy, and even chemical reactions. Once you get the hang of spotting these elements, everything starts to make a lot more sense. All right, now that we've got the basics of molecular symmetry down, let's dive into one of the most important symmetry elements, the rotation axis, also known as the CN axis. So, what exactly is a CN axis? It's basically an imaginary line around which you can rotate a molecule by a specific angle, and the molecule still looks exactly the same. The angle is calculated as 360 degrees divided by n. In other words, it tells us how many times we can split a full rotation into equal parts while keeping the molecule unchanged. For example, if a molecule has a C2 axis, it means you can rotate it by 180 degrees, and it still looks identical. If it has a C3 axis, you can rotate it by 120 degrees, and with a C4 axis, you're looking at 90-degree rotations. Some molecules even have more than one CN axis, but there's always one main axis, the principal axis. This is the one with the highest order of rotational symmetry, and it's super important because it helps determine the molecule's point group, which is key for classifying molecular symmetry. Now, spotting these axes might sound straightforward at first, but in real molecules, figuring out the principal axis can take a bit of careful analysis. So, to make it clearer, let's check out some actual molecule examples and see how it works. Let's start with an easy example. Water, H2O. Water has a C2 axis that runs right through the oxygen atom. Here's how it works. If you rotate the molecule by 180 degrees, the two hydrogen atoms switch places. But since they're identical, the molecule still looks exactly the same. That's what confirms its C2 symmetry. Pretty straightforward, right? It's a great example of how rotational symmetry works in simple molecules. Now, let's take a look at ammonia, NH3. Ammonia has a trigonal pyramidal shape with 3 hydrogen atoms arranged around a central nitrogen atom. The cool thing about ammonia is that it has a C3 axis. What does that mean? Well, if you rotate the molecule by 120 degrees, the hydrogen atoms switch places with each other. But since they're identical, the overall shape of the molecule doesn't change at all. That's why we say ammonia is a C3 symmetric molecule. Alright, what about methane, Ch.04? Methane's a bit more complicated because of its tetrahedral structure. It's not just one axis we're dealing with here. Methane actually has 4 C3 axes. Each of these axes passes through the central carbon atom and one of the hydrogen atoms. That means you can rotate the molecule by 120 degrees around any of these axes. And guess what? The molecule still looks exactly the same. It's pretty cool because it shows how methane's symmetry is a lot more complex than it might seem at first. So even though it's just a simple molecule, the symmetry here is actually pretty advanced. But wait, there's more to methane's symmetry. Besides those 4 C3 axes, methane also has 3 C2 axes. These C2 axes pass through the midpoints of opposite hydrogen pairs. Basically, you can rotate the molecule by 180 degrees around any of these axes, and it'll still look exactly the same. Now, with all these axes, you might wonder, which one is the principal axis? It's the C3 axis. Why? Because it has the highest order of symmetry. In other words, it allows for the most divisions of a 360-degree rotation while keeping the molecule unchanged. That's why the C3 axis takes the top spot when it comes to methane symmetry. Now, let's talk about benzene, C6H6. This molecule really takes symmetry to a whole new level. Because of its perfectly hexagonal structure, benzene has a C6 principal axis that runs perpendicular to the plane of the ring. What does that mean? Basically, you can rotate the molecule by 60 degrees at a time, and it still looks exactly the same. But benzene doesn't stop there. It's got even more symmetry going on. There are 6 C2 axes as well, each one passing through opposite carbon-carbon bonds. This high degree of symmetry is actually a big part of why benzene is so stable. It's also what gives benzene its unique chemical behavior, affecting things like reactivity, spectroscopy, and overall molecular properties. Rotational symmetry is definitely important when we're classifying molecules, but it's not the only thing that matters. Another key factor is planes of symmetry, also known as sigma planes. So what exactly is a sigma plane? It's an imaginary plane that splits a molecule into 2 mirror image halves. If one half of the molecule reflects perfectly onto the other, then the molecule has a plane of symmetry. There are 3 main types of symmetry planes. First, we've got the vertical plane, or sigma V. This one aligns with the main rotational axis and divides the molecule symmetrically. Next is the horizontal plane, or sigma H. It's perpendicular to the rotational axis, splitting the molecule into top and bottom halves. And finally, there's the diagonal plane, or sigma D, also called a dihedral plane. It cuts through the angles between symmetry axes. These symmetry planes are a big deal when it comes to chemical behavior and spectroscopy. In stereochemistry, if a molecule has a sigma plane, it's considered a chiral, meaning it doesn't rotate plane polarized light. This explains why meso compounds, even though they have chiral centers, are optically inactive. Their internal symmetry cancels out any chirality, so they end up behaving just like chiral molecules. To really get a handle on symmetry planes, let's start with something simple. A cube. A cube has a bunch of symmetry planes that divide it into equal halves. These planes can go through opposite faces, diagonals of each face, or even through the center connecting opposite corners. Altogether, a cube has 9 symmetry planes, which makes it incredibly symmetrical. Now, the same idea applies to molecules. Just like the cube, some planes can split molecular structures into identical mirrored halves. This kind of symmetry really affects the molecule's properties and behavior. Alright, let's see how this works with some actual molecules. We'll take a look at ammonia, water, and benzene to see how symmetry planes show up in each of them. Let's start with ammonia. It has a trigonal pyramidal shape, with nitrogen in the center and 3 hydrogen atoms forming a triangular base. Ammonia has 3 vertical symmetry planes, sigma V. Each of these planes passes through the nitrogen atom and one of the hydrogens, splitting the molecule symmetrically. But here's the catch. Ammonia doesn't have a horizontal symmetry plane, sigma H. That's because nitrogen sits slightly above the plane formed by the hydrogens, breaking the horizontal reflection symmetry. Now, let's move on to water. Water has a bent geometry, with oxygen at the center and 2 hydrogen atoms attached. It has 2 vertical symmetry planes, sigma V. One plane passes through both hydrogens and the oxygen, while the other plane is perpendicular to it. Just like ammonia, water doesn't have a horizontal symmetry plane, sigma H, either. That's because there's no clear symmetrical top and bottom half. Finally, let's look at benzene. Benzene is quite different because it's planar and has a hexagonal structure, making it supersymmetrical. It has both vertical and horizontal symmetry planes. There are 6 vertical planes, sigma V, each passing through a carbon-carbon bond. Plus, it has a horizontal plane, sigma H, that splits the molecule into top and bottom halves symmetrically. This high level of symmetry is one of the reasons benzene is so stable and has unique chemical properties. So far, we've covered rotational symmetry and mirror symmetry. But there's one more important element we need to talk about, the inversion center, also known as the I center. So, what is an inversion center? It's a point in a molecule where, if you reflect every atom through that single point, each atom shows up at an equivalent position on the opposite side. It's different from mirror planes because instead of reflecting across a flat surface, an inversion center works through a single point. It's like mapping each atom directly through that point to the other side, but the molecule still looks the same afterward. This kind of symmetry is a bit trickier to spot compared to mirror planes, but it's just as important when classifying molecular symmetry. All right, to really understand how an inversion center works, let's go back to something familiar, a cube. Imagine placing an inversion center right at the center of the cube. If you take any corner and reflect it through this central point, it lands at an equivalent position on the opposite side. It's like flipping the whole structure inside out, but everything ends up in the right place. The same concept applies to molecules. A great example is an octahedral complex. In these structures, a central atom is surrounded by 6 identical ligands. When you perform an inversion operation, each ligand swaps places with the one directly opposite. Since every atom ends up at an equivalent position, the molecule itself doesn't change, proving that it has an inversion center. Now, here's an important point. Any molecule with an inversion center is achiral. That means it doesn't show optical activity and can't exist as an enantiomer. For a molecule to be chiral, it needs to lack any symmetry elements that relate one part of the structure to another. An inversion center completely rules out chirality. All right, now that we've got that down, let's move on to another interesting symmetry element, improper rotation, also known as the SN axis. This one's pretty unique, so let's break it down. This type of symmetry operation is pretty unique because it combines 2 steps, rotation and reflection, through a plane that's perpendicular to the rotation axis. Here's the deal. It's not just a regular rotation. Instead, it's a 2-step process. First, you rotate the molecule by a specific angle. Then, you reflect it across a mirror plane. Only after doing both steps does the molecule return to its original appearance. A classic example is the S4 axis. In this case, the molecule is rotated by 90 degrees, and then it's reflected through a mirror plane. It's only after both steps are completed that the molecule looks unchanged. One important thing to remember, molecules with an SN axis are always achiral. That means they don't show optical activity. This makes improper rotation a key concept when classifying molecules and understanding their behavior in spectroscopy, crystallography, and chemical interactions. All right, that wraps up our lesson on molecular symmetry. By understanding symmetry elements like rotation axes, mirror planes, inversion centers, and improper rotations, we can better predict how molecules will behave in spectroscopy, reactivity, and structural analysis. Spotting these symmetry patterns really helps us see the hidden rules behind molecular behavior. Thanks for watching, and I'll see you in the next one.